one bank of lights. Okay. So as you already figure in this class, in chemistry, we do need to kind of talk about quantities. And what works best for us to talk about quantities is kind of to pack them up into ultimately scientific notation. So let's talk about quantities, though. Okay, quantities. Anytime you measure something, right, anytime you measure something, whether it's time or its length or its volume or its mass, you need to be able to, in this day and age, compare that same time or length or volume or mass to somebody over in China. So I'm going to kind of introduce what do we standardize our measuring equipment on. Okay, so it has to be kind of go back to something. It's interesting. I wish I knew more about history than I do. I'm kind of the older you get, the more you appreciate history. But because long ago, they're like, well, how long is it? Well, it's a foot. Okay? Well, everybody's foot's different, right? Okay? So they kind of had to standardize things. So when we talk about measuring things in science, of course, things we might want to measure are mass. The mass is the measure of how much, to me, I almost think the mass of something is an indication of how many atoms, how much material is there. Because we're going to talk about atoms, they don't weigh much, but each atom weighs a certain little bit. How much matters, a chunk of, how much stuff is in a chunk of matter. Length is the distance between 2 points. Okay, so that would be like one-dimensional, right? Area is two-dimensional, okay? And volume is three-dimensional. So volume you usually kind of think of as gallons as volume. A quart is volume. Of course, gallons and quarts are the English version of volume. And we're going to have to kind of make sure we are in the metric system. So instead of quarts, it'll be liters, okay? That's volume, how much space something occupies. And then temperature. Now, in this course, sometimes I hit temperature as just kind of a lab. And there's a good chance that I'll hit temperature as kind of a lab, kind of temperature and energy together. But temperature is not the same thing as energy, but temperature is a measure. If you have a thermometer that's stuck in something, basically you're measuring kinetic energy. Remember we talked about which phase of matter has the most kinetic energy? Gas, exactly. That was what I was after. Yeah, gas has the most kinetic energy, okay? But whether it's a gas, liquid, or solid, that thermometer is kind of getting an indication of that kinetic energy. But one thing, like the slide says you can do with temperature, is if you have two objects, let's not go with two objects, but let's go with air that's warm and air that's cold. Right now, warm air inside your house, cold air outside. One of the things that we know about that warm air, it has more kinetic energy, and it's basically going to rush out your door, okay? Even though you feel the cold coming in, okay, it's actually that warm air moving out, okay? And then there is a bit of an exchange, but so we know the direction of transfer of heat. Okay, so this then is how do you know that a kilogram here is the same thing as a kilogram in China? And if you've worked in a factory setting or a lab setting, you know that they are required, I want to say by law, by commerce, to make sure that their scales are reading correctly. Okay? And I'm trying to think, when they put gas in the like, you know, the gas stations, have you ever seen them like gassing up the gas tanks at the gas station?
Yeah, and they have the ports open in the ground.
Yeah, and exactly, and they need to make sure that that mass really is the right mass. Okay. Sometimes I think they need to check their pumps more often because I'm like, dude, that was not a gallon, but it really is a gallon probably. Okay, so my point here is road trip, go to Paris, and I'm going to show you a mock version that's in DC, but basically it's a cute little chunk of metal that we know this metal will hold its weight for a long time. But actually that piece of metal that's in a vault there in Paris, France, has been in the news in the last couple of years, and it's losing its weight a little bit. Okay. One of the things about elements is they have what's called a half-life, so they will convert, they will break down. Okay. So length, it's a tough one. To me, I could not calibrate our yardstick based upon this procedure. Okay, so One of the things about light, and light is, I'm going like this is light. You're like, really? Yeah. Actually, light is like this, but light is also like in packets called photons. But actually, light travels a certain distance in a certain amount of time. And we can use that to calibrate our yardsticks. That's a tough one. And once you have your yardstick calibrated, then you can go ahead and calibrate volume. Because even though we kind of think of volume as like a jug of milk, a gallon of milk, you can also do volume, and we're going to talk about this, you can also do volume if you have a cube. Something that has the same dimension, the width, the length, and the height is all the same. It's a cube. So how would you get volume of a cube? I think. If it's all dimensions are the same.
The length times the width.
The length times the width times the
height.
Yep, the volume of a cube. And the dimensions wouldn't have to be the same, but length times width times height gives you volume of that cube. So this is what you guys told me. Volume is equal to length times width times height. How do you get the area of a square? Length times height, or length times width, yeah, same thing. Same thing, or yeah. Exactly. Okay. So how do you calibrate your clocks? And it actually, again, goes a little bit back to light. But one feature of light is it can be broken down to its colors, okay? The different colors actually have different wavelengths. It goes like this, but the different colors have different wavelengths. Red is the longest wavelength, and violet is the shortest wavelength. But kind of along those lines, actually, one version of cesium with a mass number of 133, that's like how much it's the number of protons and neutrons in that particular version of cesium. But it will emit a certain energy, okay, as its electrons transition. And that energy has a certain wavelength, okay? And so basically not only does that wavelength have a certain length, but it also has what we call a certain frequency. So you can calibrate your watches. I couldn't do it, somebody else can. Temperature a little bit goes back to absolute zero. Have you guys ever heard of absolute zero? Okay, all matter has motion except at a temperature that's as cold as 0 Kelvin. Okay, so the temperature scale we need to use for temperature is Kelvin. Okay, so 0 Kelvin, all molecular motion stops. So that is negative 273.15 Kelvin, or excuse me, Celsius. 0 Kelvin is negative 273.15 Kelvin. Dang it, I said it wrong again. 0 Kelvin is negative 273.15 Celsius. Final answer. So you can kind of calibrate that way. Amount. Now this is kind of a fun one. It'll be a little while before we get to the concept of a mole. How many people have heard of a mole in here? Okay, awesome. Do you know when mole day is? Pi Day is coming up 3/14. When's mole day? Any idea?
Oh shoot, I have heard. Isn't it February 22nd?
It's in the fall. What's Avogadro's number? 10 raised to the 23rd. So actually, 10/23, which is October, right? October 23rd, that is mole day. Yay! Okay, isn't that wonderful? So we'll be talking more about that. But for those of you who are kind of know what a mole is, first off, do you think an atom is very big? No, it's really small. So in order to talk about kind of a set number of atoms or molecules, you got to consider a bunch of them to even kind of be able to sink your teeth into it. So basically they come up with this, it's like a dozen. How many are in a dozen? 12 are in a dozen. So if you have a mole of anything, you have 6.022, and we're going to be talking about scientific notation, times 10 raised to the 23rd power is equal to, don't do approximate sign, is equal to 1 mole of anything. Okay. So again, scientific notation we're going to be talking about momentarily, but what this means is we take the decimal and we move it over that way to make a big number, 23 places. Okay, that's one way. Just to kind of give you a sense of it, if you have, let's see, how's this work out? About 18 milliliters of water, which, let's see, 10, I'm trying to think of a 10 milliliter graduated cylinder. So basically, kind of the volume of my two fingers put together, that means you have, and it's water, you have that many molecules of water in general, if you have that volume. So that's kind of how that works. So here's the faux, this actually, it's not so faux. It's another standard, it's not Paris, it's here in DC, and it is a secondary standard. So if you've ever heard of NIST, traceable weights, basically I mentioned if you work in a factory or in a lab, they will come in to go ahead and they will check your balances with their standard balances. It won't be the one from Paris, but it'll be a secondary or a third or a fourth kind of generation standard. So, looks important, doesn't it? Okay, so measuring stuff. It's okay, there's numbers, but it's good to measure things. So we measure length, measure mass, measure time, measure temperature. So I mentioned that here in the United States, we need to be able to kind of compare data with over in China or anywhere in the world, Russia, Japan, etc. That's one of the things I like to think about scientists is, if possible, they remove the politics. They just go for the science. Okay. So we go with the metric system. So I don't know if you kind of see the metric system. So these are the standard units of length is a meter. The standard units of mass is not the gram, it's the kilogram, and we'll talk what kilo means. But the abbreviation for kilo is K, so it's kg. The standard unit of time or standard unit for time is seconds. The standard unit for temperature, I told you, was the Kelvin. Remember, like 0 Kelvin is absolute zero. Okay. So those are the international standards. So this is just a picture of some glassware that can either dispense or hold different volumes. So what are these white marks? Starts with the letter G. What are these white marks on your cylinder here? Yeah, graduations. Yep, they're just gradations or graduations, exactly the same thing. And I think you guys told me that if you wanted to have 100 milliliters of liquid, you probably would be most accurate using your graduated cylinder than you would to use your beaker. They both have gradations at 100 milliliters, but, this is the pipette that I said, never suck liquid up. Even if your boss tells you to, say, I don't think so, right? Okay. Always use a pipette bulb. This actually is similar to the pipette in that this actually is called a volumetric flask. The thing with a long neck, okay, right here. And it's similar to this sort of pipette in that up there is a mark that says to contain a certain volume. And in this case, there's also a single mark that they did at the factory to say, at the skinny neck right up there, you have a particular volume. And it's really pretty darn accurate. Usually they'll give you the accuracy of your vol flask down here. It'll be plus or minus 0.00 milliliters or something. Okay. So I think I'm going to save this one, these couple of slides, these videos, in part because I'm not feeling like my videos are going to work this morning, but they might. Okay. Measuring stuff, right? So gram is not the international standard of measuring mass. What's the international standard? Kilogram. Very good. Okay. But G is the abbreviation for grams. M is the abbreviation for meters. I bet you're fine with that. Capital L is the abbreviation for liters. And S is the abbreviation for seconds. Okay. Remember we said that volume, if you kind of put it in, you can how do I say this? You can get to the volume of something that's being contained by a cube by taking length times width times height, okay? And assuming your length is in meters, your width is in meters, and your height is in meters, can you see where meters times meters times meters is equal to meters actually cubed, meters raised to the third power? Okay, so we'll be talking more about volume. So I kind of emphasize that, you know, the only one that's uppercase is what? Liters, very good. Okay, although it's tempting, and every once in a while I'll do it. Okay, don't put a period after it, okay? Another common thing I've seen is for grams, don't put GM, it's just simply G. And I hope I'm not jinxing myself. Okay, so the abbreviation for grams is G, not GM. I see that sometimes. Okay, don't use a period. Okay, this last one up here is don't use an S. It's funny because, well, just don't use an S. What I started to say is, you know, with moles, sometimes you say I've got 6.0 moles of that. And so 6.0, but you would just put the abbreviation. I love the abbreviation for a mole because you get to drop the E. But you definitely would not put an S here, okay? 6.0 mole. All right. Everybody's favorite, the metric system. So kind of in not spending a lot of time on it. So if you need more time on the metric system, we can work that out together, okay? Or you can work that out on your own. There are some great YouTube videos out there. But I want to emphasize 4 metric prefixes that for an exam you need to know, okay? Now, unlike my other courses, you don't get to bring a note card to these tests, okay? I know, you're like, dang it, no note card. Maybe a note card on the final. That's it. So this is to say that you probably want to make sure you have these under your belt. So the prefixes you need to know, there's 1 big one and 3 little ones, basically. And you may already know these. I picked out the best ones, obviously. So you need to know kilo is 1,000 times, centi, milli, and micro. Those are all smaller, and they go in tens. So you have 1/100th, 1/1000th. Actually, I shouldn't say that. And then it skips to 1/1,000,000th. Okay. So let me kind of say what kilo means. The fact that it's 1,000 goes like this. If you have, I'm going to kind of erase these. If you have 1 kilometer, which color do I want? If you have 1 kilometer, that is equal to 1,000 meters. That's how that works. If you have 1 cute little, oops, I better finish this up. There, that's better. 1 kilometer is equal to 1,000 meters, better. Okay. If you have 1 centigram, I know we usually think of, okay. You have 1/100th of a gram. You have a piece of a gram. See how that works? If you have 1 milliliter, you have 1/1000th of a liter. And last but not least, let's go with time. If you have 1 microsecond, okay, you have 1/1,000,000th of a second. 1/1,000,000th. Well, you get the idea. Okay? So there's one more column, and I think I got this from your textbook for this figure. This other column actually then packs those 1,000, okay? It packs 1,000 up to scientific notation, 10 to the third. It packs 1/100th up to scientific notation, 10 raised to the negative second. We're going to talk about that here in a minute. 1/1000th, 10 to the negative third, 1/1,000,000th, 10 to the negative sixth. So we'll talk about those. So this actually is a figure, I think, from a different textbook. But just again, so we're all on the same page, those are the 4 that you need to commit to memory. Now, it's possible that you will have in homework dabbling in other prefixes. But do you see where always, if you look at a table like this, to me, to kind of help get my bearings, I kind of put a break here, okay? And the reason I put a break where that green line is the ones above them are larger than the base unit, and the ones below them are smaller than the base unit. Okay. So especially next week, we're going to be dealing a lot with, this is my equal sign. It almost looks like a less than or greater sign, but this is supposed to be my equal sign, okay? We deal a lot with equalities. And when I do this, this is my balance. I'm like one of those fulcrum, okay? This is my balance. We do a lot with equality statements, and that's what the equality statement is right there. So if we pick on the prefix centi, which is one of the 4, okay, 1 centimeter is 1/100th of a meter, we said, right? Okay. We can go ahead and kind of shorten the centimeter to cm, shorten the meter to m. Now, one of the prerequisites for this class was algebra, and this is kind of why. So let's say you wanted to kind of clean up that fraction, that 1/100th was bothering you like it bothers me. If I do the same thing to both sides, if I multiply both sides by 100, is that fair game? The reason I want to do that is what happens when I take 100 times 1/100th?
You divide it up, you cross them out, they all end up to be 1, so you have 1 but you.
Right, exactly. This goes to 1, exactly. Perfect. Okay. So that, and again, you'll get some work, you'll get some practice at that, but doing the same thing to both sides. So what we've got then are 2 equivalency statements that are awesome to link the unit of centimeter with the unit of meter. They're both great. If you have to pull an equality statement or equivalency statement out, either one of these will work for you. Okay. You're going to see me, I like this bottom one. This is my favorite one. I usually, for whatever reason. But either one are great. Very good. I can hear a pin drop.
Okay. Are we gonna have to, like, how they 1 inch equals 2.54 centimeters exactly? Are we gonna have to know that?
Yes.
Memorize?
Wherever there's an arrow here, and there's an arrow there's only one arrow here. There's 3 equalities you see. The other 2 equalities you do not need to memorize. You do need to memorize this equality. And there's a reason for that. Exact relationships that aren't metric are unusual. And actually next week I want to kind of talk about what do you mean by exactly? Like, isn't everything exact? No. Because this relationship for volume between the 2 systems, the English and metric system, it's approximate. Okay? You take exactly 1 gallon, and that's approximately equal to 3.785 liters. Okay, there would be other digits after that. Okay, that's a rounded number. And this other one is also approximate. So you do not have to memorize, to make sure we're all on the same page, you do not have to memorize these 2. Okay, I will give these to you. I'll put given in the problem if you need this. But anytime you see an arrow, you need to memorize. And the 4 metric things, I didn't do an arrow, but I did a box. So, okay? Very good. Another arrow. Okay, so English system, what we grew up with, metric system, what they use in Europe, and metric systems, what they use for science stuff. Centimeters, centimeters cubed. You think that's English? How many people think that's English? How many people think that's metric? Me too. Very good. Centimeter cubed. Milliliters, same question. How many people think it's English? How many people think it's metric? My point was going to be that, you know, here within the metric system, we have the relationship between milliliters and centimeters cubed. It's no big shocking thing, but I just want to kind of point that out. You need to memorize it, and it's a relationship of 1 to 1. I'll try to remember to bring a, well, this is a yardstick, and it's got English on one side, because it's a yardstick, and it's got, okay, those are inches, 3 feet. And over here is metric, okay? So a centimeter, in case you're not real familiar with it, but a centimeter is one of these major divisions. So if you take, and I've got a little box and block thing in the lab, but if you take this and you make it the same dimension on all 3 sides of a cube, that volume is 1 milliliter, exactly. Just to kind of get you thinking. All right. Scientific notation. What I started to maybe say, and I don't know if I finished that thought this morning, but the reason we need scientific notation is science, in science, unfortunately, we kind of deviate from the onesies and twosies and tens and hundreds and tenths and 1,000ths. We basically go into the very large and or the very small. And that's what scientific notation is great for. The other thing scientific notation is great for, and we'll be talking more about this next week, there's this very important aspect to rounding a number, okay? And it's called rounding, usually according to significant figures. Yes, no significant. It'll be great.
For biomolecular processes.
Good. Yeah, Mr. Salee requires you round correctly. Thou shalt not. In fact, if you do beautiful work, you know, present your chemistry work, but if you round incorrectly, you're lying. And I'll try to kind of show you how to look at your work and to round correctly. Thou shalt not lie. The conscience, you don't want that in conscience. Okay, so we'll talk about significant figures. And if your number is packed up into scientific notation, you know, blah, blah, blah times 10 raised to a power, okay, that blah, blah, blah tells you your number of significant figures. So it's kind of it's a win-win thing, okay? So you're probably already a little familiar with this. I'll go ahead and just kind of write up a number in random scientific notation. Sometimes my random numbers backfire on me. But I'll write a big number. So everything in scientific notation has 2 parts. The first part I write is a decimal part. So let me pick on 6.795. So that's my exponent times 10 raised to the 17th power. Hey, it could happen. Okay, so that's a big number, and I'll kind of talk about that. We know it's a big number because this is positive. Can you see it's positive? Okay, there's no. Okay, the small number would be maybe 4.0592 times 10 raised to the negative 12th power. And we'll talk more about this. This actually is going to be a small number. But what they have in common, my point is that they have a coefficient, okay, and then they have the exponent part, and in the exponent part, it's 10 raised to a power, and these are the powers, 17 and negative 12 respectively. All right. So, 10, it's kind of funny, I know it feels dumb, but if you have 10 and somebody says write 10, 10 is the power of 10, you would say 10 raised to the first power. I'm going to add 1 here, and some of you guys already know this. If you already know this, help me out. So what is, oh, maybe I got this wrong. 1.
10 to the negative 1.
Nope. 10 to the 0th power.
I mean, that'd be 0.1, wouldn't it?
Mm-mm.
What would be
10 to the negative first. Put it in your calculator. You have to be careful. Actually, the calculator is kind of a loaded thing. It's 1. Yeah. Anything raised to the 0th power is 1. It's a wonderful thing. Yeah.
What's 10 to the negative 1?
10 to the negative 1 is 0.1.
Yeah.
Yeah. Okay, so how are we doing with this? So 10,000, do you buy this? Or sorry, not 10,000. If we pick on 1,000 right here, okay, that's 10 times 10 times 10. And what you do is take your base times the number of times that you multiplied it by itself. Okay? Pick on 100,000 down here. 10 times 10 times 10 times 10 times 10. Okay, take your base, okay, times the number of times you had to times it by itself. Okay? All right. These are a little less intuitive. Fractions, for some reason, going small, I'm like, ew, yuck. Okay?
I hate fractions.
So 1/10, we're all kind of familiar probably with the decimal form of 1/10, 0.1. The fraction of 1/10, 1 over 10. Okay? So now here's the deal, and actually math needs to be able to handle this, and I think whoever came up with this or the way it works. Anytime you see something like something raised to a power in the, are you guys, I bet you are okay with, we call this the numerator. Think of north as the numerator. What is in the bottom?
Denominator.
Denominator. Think of down. Very good. So anytime you have something raised to a power in the denominator, you can go ahead and make that power negative, like we do here, and bring her up. It's kind of like a form of simplifying. So when we go to this one, okay, we go ahead and go one more decimal over. Of course, 0.01 is 100th. Okay, so you could write 1 over 100. The thing in the bottom, 100, we know is 10 squared. Okay, so 1 over 10 squared. We want to go ahead and resolve that thing. We don't want to deal with that fraction. We can say it's 10 to the negative second. Right? You know where I'm going next. 0.001 is 1/1000th. 1 over 1,000. 1,000 is 10 to the third. So it's 1 over 10 to the third. We want to go ahead and resolve it. It's 10 to the negative third. So if you want to go ahead and simplify a fraction, you can do that. Okay, 1/10,000th. Okay, so 10,000 is 10 to the fourth. So 1 over 10 to the fourth is the same thing as 10 to the negative fourth. Okay, and then we'll stop with this one, which sometimes my eyes start to go buggy, but that's 100,000th, right? 1/100,000th.
Yeah.
Yeah.
My-
Are we good with that? I thought so. Okay, so let's start with packing up numbers in scientific notation. Packing up. So is this a large or a small number?
Large.
Large. So it's going to have a positive 10 raised to a positive, okay? So that's actually how I usually think of it. So first off, you want to get a number that is between, how do I say this? Between, it's greater than 1 but less than 10. Okay, so this is your coefficient. Okay? Do you see where I got that from my main number? Okay. Then the other thing is, well, if we go with 4.55, how do I go back and get my main number again? And the answer is, in this case, you multiply it by 100,000. So one of the things a few slides ago, we said 100,000 is 10 to the fifth. So here we have the number packed up in scientific notation. The coefficient is 4.55. The exponent part is times 10 raised to the fifth power. Okay. I have the other, here in a minute, some of you probably have learned it with you sink the decimal point, you do it in stone, and then you count how many places you had to go to, and I have that way coming up. Okay, so let's look at You think this is a large or a small number? Small. 0.0021 is small, relatively small. So trying to get a number between 1 and 10, it's looking like I'm going to deal with the 2 and the 1, but actually it's going to be 2.1. Yes, 2.1 is going to be the coefficient, exactly. And as some of you know, you have to move the decimal place over 3 places. You can also think of it as 2.1 times 10 to the negative, times 0.001. Kind of break it up. And then what is 0.001? That is 10 to the negative third. Okay, so this is these are a pair of numbers packed up in scientific notation. So you're going to get some practice at that this week and for homework that's due. Okay. So I have a couple of slides to kind of summarize what we just did, basically. This first one is writing numbers that are large, okay? Let's just go ahead and cut to the chase. Many of you have learned it well. If I have a number like 3, 4, 5, 0, 0, 0, 0, 0, 0, 0. Woo! Rather large, isn't it? Where am I going to put the decimal if I want to pack it up in scientific notation?
3.45.
Exactly. I'm hearing it good out there. That's where I'm going to want to put it for my coefficient. Where is it right now?
At the end of the 6th zero.
It is right now. And actually, we're going to be talking more about this next week, but I'm going to go ahead, and you're right, I'm going to put the decimal there, but it's not clearly stated there. It is, I'm going to go ahead and write the word implied. Implied. And if you think you know what implied means, you do. Implied is like, ooh, you know it's there, but no one took the time to put it there. Okay, there's a subtle difference. Sometimes they put it there, sometimes they don't. So,
Understood.
It's just understood. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Reasonable? Okay. So I'm liking, what's my coefficient going to be?
3.45
Yep.
times 10 to the 9th power. Yay! I do remember some stuff from algebra.
Yay. Very good.
I'm glad I'm actually taking it at the same time. This is actually
Good.
better that I'm taking it at the same
It's been
time.
a year and a half since I took algebra. I'm just in math for liberal arts right now.
Well, let's go ahead and do this other one. I think it works whatever, so I'm just glad you're all taking this class.
It's always a good to have a refresher.
It is. So let's take something that's small. Let's go 0.000000. So let's look like I have what we call leading zeros, 6 leading zeros, 7092. Woo! Jeez, I know. Okay, so where am I going to move the decimal place to in order to get my number between 1 and 10?
Between the
7 0.
Yep, I'm liking that. This is my new place for my decimal. Okay, and no implication required here. I know. 1, 2, 3, 4, 5, 6, 7.
So it'd be 7.092
Okay.
times 10 to the negative 7.
So what's my coefficient going to be?
7.092.
I'm liking it. Times 10 raised to what power?
Negative 7.
Negative 7.
Yes.
Any questions? Stands for quite easily done.
I'm like, what?
I think. Okay.
Never heard that on Big Bang.
So 10 raised to the 0th power is 1. We're right. Anything raised to the 0th power is 1. It's like an identity thing of powers of 0. Okay. So if somebody's being silly and they give you a number that's between 1 and 10, like 3.236, and they might, who knows? Grad entrance exam, I don't know. And so if they say, I want it scientific notation, you're like, all right, fine. The coefficient is the same number, 3.236 times 10 raised to the 0th power. You're like, there you go. Go to it. Okay, so you guys have a few on the next slide. Go ahead and take a stab at those. And after you have, see if we agree. Goodness. If you're like me, you have to like see them. You have to physically move the decimal over.
That last one's confusing me.
For something that's negative, you make sure that that tags along with the coefficient.
Be negative 4.4.
Yeah, that third one is a good one. The negative tags along. Are there any? So I went ahead and checked your answers up there.
So, and then like for that last one, because the negative stuck with the 4.4, that's why the exponent is positive.
There's two different things going on with that last one. We're not quite done. I got 15 seconds. So the thing about this one is the negative stays with the coefficient because it's a negative number, but the power of 10 is positive because it's larger than 10. Okay, so these, you have the assignment slide, right?
Yep.
Okay, so this is actually then what you're going to be tasked with. Looks like this. Now, they come in pairs in your textbook. What does the blue mean?
Odd answers are in the back of the book. to check,
Yes,
so.
the answer's in the back of the book. So you need to do 32, 34,
36 and 38.
36, and 38.
The ones that aren't in the back of the book.
Exactly.
Dun dun dun.
Okay, any questions? So those will be due Monday. Have a great weekend. Dun,
And
dun,
it's okay to
dun.
hang on to those calculators.